Hey everybody, and welcome to another episode. First of all, I have to say that maybe my sound sounds a little bit weird. My voice sounds a little bit weird. It's not about your headphones or so. I just have a sinusitis, I think it's called, and that's why I sound a little bit weird, so I apologize for that. Now, today we are going to talk about this object here. It's the comet called Atlas, and it's an interstellar object that is coming from interstellar space with a very high eccentricity, so a very hyperbolic orbit, passing currently around the orbit of Mars, where all the spacecraft are pointing at it to obtain some data. And then quite fast, it will also disappear in the vastness, in the void of the cosmos. But the thing is, why are we taking a look at this, and why are we also creating a short Python function to compute the velocity? Well, the thing is that the velocity was the major point of a very speculative debate of some scientists claiming that this comet is of interstellar origin, yes, but of artificial interstellar origin. And well, I know this topic is then hyped and people are talking about it because a scientist is talking about this, claiming things without any evidence, and that's not very scientific to make any claims without having any scientific proof, because at the end of the day, we have to use Occam's razors that states that, well, if you have different models describing a certain phenomena in nature, then you have to choose the model with the less parameters that are, let's say, that describe the problem. So, long story short, if an object appears as a comet and moves like a comet and, well, has also the shape of the comet, it's most likely a comet. So that's maybe part number one. And the second part is that don't fall into the argument fallacy of argumentum ad verecundiam. It's an argument that states that, well, people are weighting the opinions of experts higher, or of authorities, because they have a certain authority. I'm not denying any authority here in this regard. I'm just saying that with Occam's razor and with this logical fallacy in mind, we should maybe reconsider the hype a little bit and think of the comet as a comet. So without further ado, I would say let's switch to Python and let's take a look into the velocities. Is this really that weird? Yeah, and let's compare it with the other two comets as well, so that we have an idea whether this kind of argument, well, that the velocity is too strange to believe, makes sense or not. So let's go. So very well, we can go now in our coding session, and first of all, everything is of course stored on my GitHub repository, so the link is in the description. You simply click here today on compressed cosmos, then you go to compressed cosmos _ interstellar comets, and there you find the Python notebook. You simply click here on open in Colab, and a Colab tab will open with the entire code for you to work on. Now, first of all, today's code is very, very short, and it is more the mathematical stuff that I would like to show you, because the very first equation I would like to use to show you to how to compute the velocity at the perihelion of an object is the Vis-Viva equation. So this is like the velocity squared is equal times g times m. So g is the gravitational parameter, the gravitational constant, and m is the mass of the center body. So in our case, it's the sun. R is the distance between, for example, the comet and the sun, and A is the semi-major axis of the comet. Now R needs to be replaced by something that defines the perihelion, and the perihelion is simply the semi-major axis times 1 minus E. We simply substitute it, do some very high school math, and then we have the equation here at the very bottom. And that's something we want to take a look at for 3 different comets. Now, first we need to connect to an instance. If you get some kind of warning because this is a GitHub repository, then you have to click whether you trust this code or not. I think my code is quite trustworthy. You can already, of course, always check it. And then in the very first cell here, we define our constants. The yeah, here we have the arrow, the gravitational parameter and also the mass. I took the values simply from Wikipedia, also the semi-major axis and eccentricity from Oumuamua, the first interstellar comet, Borisov, the second one, and Atlas. And you see, for example, the eccentricity, how it increased with all the with all the discoveries. Like the Borisov was already 3.3, and now with 6, we have almost twice this value. And of course, people think like, oh yeah, this is so high, the corresponding velocity is too unrealistic. Let's see whether this applies or not. Because in our second part, we simply define the function we just wrote down here. So kind of, I would say, no rocket science involved. And then what we do afterwards is simply execute in the last cell the functions for each comet for the corresponding semi-major axis and eccentricity. And we see here the results for Oumuamua, Borisov, and Atlas. And we even see that Atlas' perihelion velocity is even lower than the one from Oumuamua. So these are velocities that are, I would say, they are high, yes, of course, but they're not unrealistically high. It's not unrealistic what we see here, so it's something that makes totally sense, and there is no need to have another explanation, but it's a natural comet, probably ejected by some kind of astrodynamical mechanics in the past. How this mechanics could look like, we will do this kind of simulation or try this kind of simulation in Universe Sandbox soon, but you see these numbers, they are not suspiciously high or whatever this means. So let's stick with these values. Now that's a very, very short video today. And as you saw, the velocity of Atlas is not outrageously large or something, or suspiciously large, or whatever this even means. Even Oumuamua was faster at the perihelion than Atlas today. Now, I do not understand the arguments of different or strange velocities or so. You can simply compute the velocities with orbital elements. There is no need to add anything artificial or so or something like that to explain the orbits. The orbits, the orbital elements, as I just showed you partially here, are given based on the observation. So we do not have to make the interstellar objects more fancier than they are, because it is tremendous that we are able to see these objects, and there are even speculations that Atlas is between 7 and 10 billion years old, and I think even this scientific discovery is really worth mentioning and being fascinated that we are able to experience this scientific insights in our lifetime, and there's really no need to make it higher or fancier or more mystical than it already is. It is truly amazing what we can achieve when we all work together in space missions. See you next time.